introduce Neal. Neal got his PhD from Berkeley in physics. Then went on to be a postdoc at Caltech before joining the faculty at the University of Texas. He's now the, got the name already. What is it?
Edward Randolph Jr., MD, Centennial Professor of Astronomy.
Thank you, Jeff. Hear that? A whole bunch of names thanks to a big donor.
Yeah, it sounds like
it's going to talk today. Today. Talk about that as soon as we can get the mic turned.
Yeah, I don't think it's working. Well,
hit it.
You can hear it. Okay. All right. All right. I tend to wander around. Yeah. Okay. How does that? Hear me in the back? Okay.
And as usual, we will present Neal with the customary, now not nearly good enough, memorial present, named merely green laser pointer.
I was expecting maroon. I don't know.
We'll look at that.
All right. Okay, so it's a pleasure to be here, and absolutely great to hear the news about GMT. This is one of those things that we're doing together, and I think it's really important that we continue to work together on these things. Is this microphone actually working? Okay, all right. Okay, so why talk about star formation? So we have now, amazingly to me, a precision cosmology. Simulations can explain large-scale structures, so we get basically gravity and expanding space seems to work pretty well. When you get to galaxies, which are composed of stars, gas, black holes, not so good. We don't really understand that formation and evolution. So for a full picture of cosmic evolution, we need to understand star formation. So just from precision cosmology for a moment, this is not my field at all, but I think it's remarkable. When I started in this field, there were people arguing about that age of the universe, the factors of 2. And now we're talking about decimal places. Pretty amazing. This is an old pie chart, but newer numbers from the Planck 2015 are over here. So we kind of know there's all this stuff, dark energy, dark matter, and then a little bit of baryons. We don't understand what those are, but we know with high precision what the fractions of these things are. And when you put that kind of stuff into a simulation, this is just one of them, you get this web of dark matter, and the dark matter collects baryons, and all that seems to match what we see very well. When we come to galaxy formation, it's not quite so good. This is just an old, oops, say that again. This is an old simulation, but it gives you the idea. In this dark web of dark matter, baryons fall in and they make galaxies, and there's various problems with this. So what are the problems with these simulations? The gas cools very rapidly. It forms stars with high efficiency and produces galaxies that are too massive. And we also find out that most baryons are actually not in galaxies. These are just some quotes from a recent paper by Phil Hopkins about this, the current issues in understanding galaxy formation and evolution. People here can talk about this in much more detail than I can. So the usual solution is to invoke starvation and feedback. So you starve the galaxies of gas, so it doesn't fall in right away. And once it falls in order to prevent it from forming all into stars really fast, you have the stars and other things blow most of it away again. Now that's probably all true, but most simulations of star formation on the scale of galaxies or the universe take a very simple model of star formation. So let me try to walk you through that simple picture first, and then we'll talk about some of the complexities. So this is star formation is simple. So at the simplest level, it's basically a fight between gravity and thermal pressure. And if you ask at what point those balance each other, and there are various ways you can do this, but you basically get something called a Jeans mass. And that in useful units is about 18 times the mass of the sun times the temperature. to the 1.5 power and divided by the square root of the particle density. Now, as I'll show you later, stars form in molecular clouds. In molecular clouds, the temperature is about 10 Kelvin, and the particle density is more than 100 per cubic centimeter. So if you plug those in, you find out the Gene's mass is less than about 60 times the mass of the sun. And if you look at the spectrum of masses of molecular clouds, all the mass is in clouds much more massive than that. So simple physics says these should be collapsing. So how fast should they collapse? Well, if you approximate them as spheres, like we always do, the gravity grows with radius. And if you work this out, it turns out the outer shells are going to fall in faster. And so what happens in a uniform gas sphere is that all the shells reach the center at the same time. And this time is called the free fall time. And the equation for the free fall time is another very simple physics situation. It's 3.4 times 10 to the 7th years divided by the square root of the density. So since I said the density in molecular clouds is at least 100 per cubic centimeter, you wind up with 3.4 million years as kind of the largest your free fall time is going to be. So how does that work out? The total amount of molecular gas in the Milky Way galaxy is about 1 times 10 to the 9th solar masses. So if you put those two numbers together, you get a star formation rate that's more than 290 solar masses per year. And the observed rates are somewhat less than that. If you average over the lifetime of our galaxy, just take all the stars in the galaxy and divide by the lifetime of 10 gigayears, you get about 8 solar masses per year. So that's the average rate at which we had to form stars over the history of the Milky Way. And the average over the last gigayear or so is more like 2 solar masses a year. So things are slowing down in our galaxy. But right now, the mass of molecules in the galaxy divided by the free fall time gives you a number like 290. So it's way too big. So the simple physics isn't quite right. Now the funny thing about, this comparison is for the universe, we know with high precision these numbers, but we don't know what dark energy and dark matter are. Here we know all the physics. This is all simple physics, but we get the answer wrong by a factor of about 100. So what's going on? And the problem is that turning gas into stars involves much more than just gravity. The interstellar medium, which is the technical name we give for the stuff between stars, is multi-phase. There's some of it that's really hot and low density, and that doesn't form stars. There's stuff that's intermediate densities and temperatures, and that doesn't form stars. And so only part of it, the molecular gas, forms stars, but we don't have a really good theory to understand what fraction of it is in this molecular form. And one of the most, as Darren said, I was a physics grad student. I only took one astronomy course. But the one thing I remembered from that is this fact here, that in the interstellar medium, there's 1, 2, 3, 4, 5, 6 things of roughly equal energy density. So thermal energy, turbulent energy, magnetic energy, cosmic rays, stellar radiation, and cosmic radiation all have roughly equal energy density. So right away, this is not a simple problem. Now, it could be that many of these things are coupled, but the fact that it's similar to the cosmic background radiation energy density is probably a coincidence of the particular time we live in. But it's nonetheless a warning that things are complex. On top of that, stars do provide feedback. So it's not as simple as just saying whether things collapse or not, because there's a feedback process. When some stars form, they're going to affect the ability of other gas to form stars. So here are the fundamental questions. Galaxies don't form all their stars immediately. Some galaxies form stars in bursts. Others, especially some of the nearby dwarf galaxies, are sort of just getting going on forming stars, whereas some folks here and at Austin are looking at stars that are forming only half a gigayear after the Big Bang. So there's a huge range in when galaxies form their stars. So all this says we need to understand what controls the rate of conversion of gas into stars. And the theory is lagging in this area. So there's a lot of focus on empirical laws. And I don't particularly like to call them laws, but that's what they're called. So we'll talk a little bit about the basis for some of these relationships, which is what I prefer to call them, about observables and star formation. So that's kind of a little background on what are the underlying issues that we're trying to deal with here. So if we start with the biggest scale, this is the cosmic star formation rate from an annual review article from 2014. And if you look versus redshift or the other way around, look back time, you can see that the rate of star formation is increasing. These numbers are pretty uncertain. You know, people here are working on these points here. But it looks like star formation really hit its peak about 10 gigayears ago, or about 3.7 gigayears after the Big Bang, and has been declining ever since. So this part we know reasonably well. This part certainly needs a lot more work. But pretty clear that there was a peak in the star formation rate in the universe. So that looks pretty simple. You might say, well, that's a pretty clear picture. But this is large scale, sort of averaged over everything. If you look at individual galaxies, you see an enormous diversity. This is from an annual review article I wrote with Rob Kennicutt a couple years ago. And if you plot the log of the star formation rate, we use that symbol a lot, in solar masses per year, and on the y-axis you put the surface density of star formation rate. So star formation rate divided by area. And you see that on both these axes you have an enormous spread of like 6 orders of magnitude. So galaxies form their stars in really different ways at different rates. My contribution to this figure was this point right here. So I work on star formation in the Milky Way, and if you see the Milky Way, well, it's sort of sitting at pretty high star formation rate among the group of sort of purple points, which are normal galaxies, so to speak, not starbursts. If you go up to higher star formation rate or up in surface density, so more concentrated, that's where the infrared starburst galaxies live. Well, there's a lot of points on here, but the point here is the enormous spread in both axes. Now, if you plot instead, well, this figure is really bad. This is the surface density of the star formation rate, and on the x-axis is the surface density of gas. And then all that diversity collapses into a pretty good relationship, and this was plotted by Rob Kennicutt in his previous review of this subject in 1998. And it has really informed a lot of what goes on. So this is often referred to as the star formation law. Now, it's important to understand that down here we're talking about normal galaxies like the Milky Way, which we abbreviate with spirals. And up here we're talking about starbursts. So they're really kind of two different sets that are defining this relationship. And at some level, this is what you'd expect because we believe that stars are made out of gas. So higher surface density of gas, higher star formation rate. That makes sense. The interesting point about this is that the slope of this fit is 1.4 plus or minus 0.15. This is a new version of that, which we put in our paper. Again, I added 1 point here. And this is the log of the star formation rate, surface area, plotted versus the surface density of gas. And so this is the original, the line is the original 1.4, not been refit. In fact, a little hard to see, but it goes through there. And then you see there's lots more points now, and they kind of agree with that original thing that he did more than 15 years ago. You do see some discrepancies. For example, these blue open circles, those are galaxies with low metal abundance, not so many heavy elements. I remember for astronomers, heavy elements are anything but hydrogen and helium. And down here at this end, these are mostly, these are falling below the fit, which goes down there. Okay, so at low surface densities of gas, something happens. And that point's about 10 solar masses per square parsec. Now, to explain a little bit about this axis here. This is the surface density of all the gas, and by all I really mean some of the gas. It's the gas that's atomic hydrogen, so that can be probed with a 21 centimeter hyperfine transition. and it's the molecular gas. So the molecular gas is mostly molecular hydrogen, but you can't probe that gas by looking at lines of molecular hydrogen because molecular hydrogen lines are too hard to excite. The hydrogen's a light molecule, so its rotational transitions lie in the infrared, and the temperatures that molecular clouds are, you don't get things into excited states. So this is probed with the second most common molecule, which is carbon monoxide. And then you say, okay, for a given strength of emission of carbon monoxide, I convert that into a mass of gas. Now, the abundance of carbon monoxide is about 1 part in 10 to the 4th. So you're making an extrapolation, and that alpha there is sort of defining that. So we're assuming that that's the same for all galaxies in this plot. Okay. That might give you a little clue about why these metal-poor galaxies, remember C and O are metals, lie off to that side. Okay, so the dependence of the gas to the 1.4 power provided an irresistible temptation to theorists. So the 1.4 is about 1.5. I said my simple argument before was the star formation rate should happen at the free fall time. So if I take the mass, divide by the free fall time, that's a reasonable approximation of the star formation rate. Or I can think of the surface density, which is what we can measure easily. So the surface density of star formation rate should be sort of like the surface density of gas divided by the free fall time. Or I go all the way down to the volume density and say that should be the volume density of gas divided by the free fall time. And so the free fall time depends on 1 over the density to the square root. So I get a 1.5, okay, which is the same as 1.4. I put that in my code. I recover the Kennicutt-Schmidt relation, which is what that relation is called, and I understand everything. Now, this is obviously circular, but I am not kidding you. I've seen talks where people do exactly that. And there's one little problem. The star formation rate is 100 times too high. So you fix that by putting in an efficiency for free fall time of 0.01. As far as I'm concerned, that's a fudge factor, but theoreticians believe it. Or you say, okay, it's quenched by feedback, and we only turn 1% of the stuff into stars, and then we throw out the rest of it. Okay, so that's kind of one of the leading theoretical ideas, and here's a plot from a paper by Mark Krumholtz, Avishai Deckel, and Chris McKee, who are really the leading lights of theory of this stuff. And I don't know why the resolution. Yeah. Anyway. This is the surface density. This is the same plot, surface density of star formation rate there, but on this axis now, it's the surface density of gas divided by the free fall time. And so this now should be a linear relationship, and there's a whole bunch of galaxies, molecular clouds, and so forth, and yeah, it follows the curve, so it looks pretty good. We'll come back to this. So where do stars actually form? Let's take a closer look at this story. So first, let's look within galaxies. There's a lot of recent studies of other galaxies that are starting to probe not a total star formation rate in the galaxy, but probing on smaller scales. And we use the term is kiloparsecs. We live about 8 kiloparsecs in the center of our galaxy. So if you go to sub-kiloparsec scales, you're looking at local regions within a galaxy. So there's a whole alphabet soup of projects to map out various tracers in nearby galaxies and separate the gas into atomic and molecular components. So this is some slides I got from Eva Schinnerer, who's led a lot of this work. M51 is one of the nearest face-on star-forming galaxies that is a good thing to study these relationships in. And this is a map of the atomic hydrogen. And you can see that there's something that begins to look kind of like spiral arms there, but there's a lot of stuff in between the arms. The contrast is not super high. Now, Eva has spent untold hours mapping this out in carbon monoxide. So if you map in carbon monoxide, you see a much sharper picture with the spiral arms much better defined. And there is stuff between, but the bulk of material is in these spiral arms, and there's a concentration at the center. And if you look at where star formation is happening, this is a 24 micron emission from the Spitzer telescope. And the resolution is not so great here, but you can see this very well outlined regions of star formation along the spiral arms close to where the molecular gas is. And this is hydrogen alpha emission, also tracing H2 regions where stars have ionized the gas. And the carbon monoxide is shown in contour, you might be able to see. And you see there's some offset there because once you form a lot of massive stars, it destroys the gas, but you see that it follows along the molecular gas very well. And if you look at this more quantitatively, this is a plot from Andreas Gruba, and this is a map where you essentially do azimuthal averaging, and you go out in rings of radius in another galaxy, and you ask, what's the atomic hydrogen doing, which are the gray points, and what's the molecular gas doing, which are these green points, and then it's continued on with some orange points and upper limits out here. And then you ask, what's the star formation doing, and you see the star formation follows the molecular gas, even out into a region where there's 10 times more atomic gas than molecular gas. So it's very clear that star formation is associated with molecular gas, not just any gas. So, this is a plot from the same group, again showing the surface density of the star formation rate versus the surface density of both kinds of gas. And you can really see now, or you could see, a drop there at about 1 here, which is in the log scale, that's about 10 solar masses per square parsec. And so there's a definite drop, and that is the point where most of the interstellar medium is atomic rather than molecular. So when you wind up in a totally atomic-dominated medium, star formation drops off dramatically. Now, there's another relationship that was found by Gao and Solomon, and they looked at the star formation rate versus the amount of dense molecular gas. And the way they did that was by using a different molecule from CO, a molecule called HCN. And HCN is harder to put into excited levels than CO is. So it tends to emit only in relatively dense gas. And so they found a linear relationship, not the 1.5 slope, a linear relationship between the star formation rate and the amount of dense gas. It has smaller scatter and the higher star formation rate per amount of gas. So the efficiency for dense gas is constant. The star formation rate per unit mass is constant. That's what a linear fit means. And high, higher than for the molecular gas as a whole, certainly higher than for the sum of the molecular and atomic gas. So if you look at this plot, this is the log of the star formation rate versus the log of the surface density of gas. And these are all these different relationships I've talked about. This is the Kennicutt relation, which is the nonlinear slope. This is the slope when you look in nearby galaxies on sub-kiloparsec scales, and I've plotted the range where it's actually measured, and then I've extrapolated. And this is never mind the yellow points right now, I'll explain those later. This is essentially the relationship that's found for dense gas in Starburst Galaxies. That's the only place where you really have done this study. And you see that extrapolates down, so they don't really overlap here. But the Kennicutt, you might then begin to think, well, is the Kennicutt relation really an amalgam of these kind of guys down here forming stars linearly proportional to the amount of gas, plus these starbursts, which are forming stars up here? So I'm going to now zoom in to the Milky Way itself, which is where I tend to work. And we now have surveys of the Milky Way at sub-millimeter wavelengths. So these are measuring the amount of relatively dense gas through the fact that dust is mixed with this gas, and the dust emits at these long wavelengths around 1 millimeter and a bit less. So this survey is actually done at 1 millimeter, 0.85 microns, and it covered the southern part of the Milky Way, done from Chile. And another survey that we were involved in covered the northern part, And this is just to give you a feel for what it does. The red stuff here is where the dense gas is. The green stuff is what Spitzer sees, and this purple stuff is radio, and this is some of the stuff going on at the center of the galaxy. So I don't want to dwell on this, just give you an idea of what's going on in our galaxies. When you look at a different wavelength, you see different aspects. So the infrared Milky Way, this is essentially the center of the galaxy again, and with Spitzer, we were able to map out the galaxy. This is sort of going out this way, and then farther, and then farther. And you can see there's less activity as you go farther out, but all this stuff is reflecting, all these things here are reflecting regions of intense star formation. So we have right close at hand a place where we can study in much more detail than you can in other galaxies what goes on when stars form. So this is a result of the survey of the northern sky. We haven't done the southern yet, in which the problem with studying our galaxy, let me go back a sec, is that we live in the plane of our galaxy. So that means when you see something in a certain direction, you don't know if it's somebody in the front row or somebody in the back row. So we have a real problem sorting out the distance of the things that we're studying. So a huge effort by a really good grad student at Colorado has sorted that out for a large fraction of those regions of star formation. And here's the sun, here's the center of the galaxy, and you can see there's a lot of stuff, there's a lot of dense gas right here where the bar in our galaxy ends and a spiral arm begins. That's a region of intense star formation and lots of dense gas. There's also an arm back there that has a lot of dense gas. You also may notice that there's a lot of dense gas that's actually between that arm and the bar, and we're not sure whether that's problems with our distance estimate or whether it's problems with this model, which is, after all, only a model of our galaxy. So there's interesting work going on there. But we're tracing relatively dense gas. Remember, for those of you who work in the labs, when we mean dense in the interstellar medium, it's better than your best vacuums. We're talking about 10 to the 3.5 per cubic centimeter. That's relatively dense. Okay, so we know where this stuff should be forming stars based on what we said before. Dense gas correlates well with star formation. So I have a student now who's just finishing up, and she took that data, which is shown here for a chunk of the galaxy. This is essentially galactic longitude if you look along the plane of the galaxy, and this is perpendicular to that. And there was a satellite called WISE, which surveyed the entire galaxy at 22 microns, which is supposed to be a star formation rate tracer. So she took the 22 micron emission and 1 millimeter emission. This should be the dense gas. This should be the star formation. You kind of get the feeling there's some correlation. Here's just another chunk. And plotted these up. So this is that same relationship we keep showing, the Kennicutt-Schmidt relation for the 1 millimeter emission. Now should be tracing the denser gas. So this is tracing the denser gas surface density on this axis. Again, star formation on that axis. Here's the Kennicutt relation. And what you get depends a little bit on what your resolution is. So she did a series of smoothings, basically simulating lower resolution as you would get if you looked at another galaxy. And essentially all the points lie well above this Kennicutt relationship. So the Kennicutt relationship in this view would be emerging out of averaging over regions that are forming stars and regions that are not forming stars. And if you look at a region that is forming stars, you get a value above that. Now, there are some limitations. I mean, I mentioned the line of sight averaging here. We don't have information on the distance to these 22 micron emission things. And, yeah. And it's the best, that's right, the best fit is linear, or sublinear even. But we have to worry, does the 22 micron emission really trace the star formation rate? So she also did a study in which she looked at the infrared star formation rate traced by infrared emission. And the idea there is that the stars put out a lot of light. The light's absorbed by dust. The dust irradiates it in the infrared. That's the basis of all these infrared star formation rate tracers. And looked at that versus the the actual logarithm of the luminosity in the infrared. And plotted the ratio of the star formation rate you get from using the same relations that are used in all the extragalactic studies to our best estimate of the star formation rate. And for luminosities above about 10 to the 4.5, they agree. The ratio is 1. Below that, the star formation rate is grossly underestimated by these tracings. And the reason is that these regions are not forming massive stars. And to have the infrared trace the star formation, you have to be forming the entire function of masses of stars. So this kind of star formation would be completely invisible. The star formation down here is completely invisible to extragalactic studies of star formation. Okay, now, we look for still denser stuff. I had another student who went and did follow-up studies at shorter wavelengths and found the surface density substructure within those 1 millimeter emission peaks. So some of these are getting up to cross certain thresholds which are believed by the theorists to indicate that you really get massive star formation, you really begin to sample the entire mass function. So if we go and look at those are the yellow points on this plot that I showed earlier. So these are regions of massive and dense regions in our galaxy that are forming stars all the way up to massive stars. These are even denser, 10 to the 5th per cubic centimeter. And this is work by a former student, Jingwen Wu. But my current student has now checked these star formation rates by using radio continuum, which is another way of measuring the ionizing photons put out by the most massive stars, and it agrees with the far infrared. So those agree, and we see a much higher efficiency than you get from these relations, which are based on either total gas or even molecular gas. So the denser the gas you look at, the higher the efficiency. And these are the things we were just looking at, the massive dense clumps in our own galaxy, and these are the Starburst Galaxies that Gao and Solomon used to get the relationship between star formation rate and the amount of dense gas. And you can see these are separate fits, but you can see they're both linear. The slope there is 1 in a log-log plot, and the offsets are very similar. So it looks like the Starburst Galaxies are completely consistent with being a whole bunch of these dense clumps, just like we study in our galaxy. And that works until you get down to a luminosity of 10 to the 4.5, at which point the thing falls apart because you're not sampling the massive stars anymore. Okay, so let's take an even closer look. So this is the same Milky Way. This is all the points that went into that plot I showed you earlier. But now let's zoom in to the local region around our own sun. In that region, we did a study, a project with Spitzer, in which we mapped essentially all of the nearby clouds, completely looking for infrared point sources. So now we can actually count the number of stars. And we can count them down to basically 1/10 of the mass of the sun. So we really are not missing things. And so we just count the number of YSOs and divide by the lifetime. Oh, sorry, more jargon. YSO is young stellar object. So it's something that's not a star yet, but it's becoming a star. And you divide by that lifetime. And that gives us a star formation rate. So how does that star formation rate depend on cloud properties? Okay, here's that same picture. You've seen over and over again. This is the sum log of the surface density of star formation rate versus the log of the surface density of gas. Here's the Kennicutt relation. This is the relation in nearby galaxies. And you see that almost all of our points lie well above, typically an order of magnitude above. And now we're measuring the surface density of gas based on actually the extinction through the cloud. So using the dust as it absorbs light to measure the amount of gas. So we don't depend on knowing how to convert from CO. So we have, again, a higher star formation rate than the extragalactic, quote-unquote, laws would tell us. So if you plot the star formation rate per massive cloud. So this is essentially the, how efficient is star formation going on. There's a big scatter. This is plotted versus the mass of the cloud, the log of the mass of the cloud. And it scatters all over the place. And Charlie Latta did the same thing, different kind of analysis, but the same basic result. This is the number of young stellar objects over mass. This is cloud mass. And again, they're scattered all over the place. So a bigger cloud doesn't necessarily have form more stars. So remember this plot? This is the one where the theorists had said, okay, I just take the surface density and divide by the free fall time, and I'll get the surface density of star formation rate. So let's look at that on the scale of individual clouds. Does that work? Their claim was that this global thing that you see in galaxies is actually built up of a whole bunch of relationships within individual clouds. So let's test that. Does the star formation rate of a cloud depend on the free fall time of the cloud? Now, remember the free fall time depends on 1 over the square root of the density. But the way you get the density in their picture, you take the whole cloud and you divide by the volume. Mass of the cloud divided by the volume. So you're taking an average density. Now you know that the average of something is not this, 1 over the average of something is not the same as the average of 1 over something. So this is a problem right away. And what you find is that the theory with, let's get the right hand here, with this fudge factor of 1%, kind of gets the general value right, but that's by construction. They knew what the answer was. Do they actually correlate? And the answer is no. That correlation is not statistically significant. So where do stars actually form? So this is kind of a whole cloud in the Perseus constellation. And when you actually plot all the stars, the young stellar objects, which are the red points there, you see they're very highly clustered. And they're clustered in regions of high extinction, that is, regions of large surface density. So only 9% of those things are outside a contour of 1 solar mass per cubic parsec of stars, of young stellar objects. And the ones that are distributed are actually the more evolved ones. So they could have wandered there because the time to cross out of the dense regions is about the same as the lifetime. So we focused on the younger ones, the ones that are only maybe 500,000 years old, so that they're still associated with their birthplace. Now, what we've learned since then with the Herschel Space Telescope, which maps huge chunks of the galaxy, is that all these molecular clouds are not spherical at all. They're very filamentary. This is a Polaris cloud, and you can see a lot of filaments in it, but no stars are forming in this cloud. Plenty of molecular gas, lots of molecular mass, no stars. If you go to a different cloud that's got filaments which are denser, and all the blue triangles here are places where there are small, dense cores that are the precursors of individual stars, you all lie along filaments that have a higher than a certain threshold extinction. This is another bit of jargon. We measure the extinction at visible wavelengths in magnitudes. And essentially that is a threshold of about 8 magnitudes. If the filament gets a higher extinction than that, which you can translate directly into surface density, then you begin to form stars. So the proposal is that stars form above a certain threshold in surface density, and that was made independently by Charlie Latta and a former student of mine, Amanda Heiderman. And Charlie's plot is this one. He plots the number of YSOs versus the cloud mass above some threshold. He plots that for a whole bunch of thresholds, and he asks, where is the dispersion the least? Where is the kind of critical surface density where I get the smallest dispersion in these values? And the answer was 116, plus or minus 28, solar masses per square parsec. That roughly corresponds to that AV of 8. So he proposed this star formation relation. Just star formation rate's a constant times the mass of dense gas. So what if we test that in our clouds? This is the same plot I showed you earlier where there were points all over the place. This is now the star formation rate per unit dense gas mass versus the log of the mass of dense gas. By dense here we mean above this threshold surface density. And you can see that the dispersion is now very small. It's comparable to the systematic errors. So within the systematic uncertainty, which is about a factor of 2, you get the same answer for all of these clouds. So if you focus on the dense gas, you get a very tight and nice relationship. And essentially, since we're plotting surface star formation rate over mass, a flat thing here is equivalent to a linear thing in the usual plots. Now, we have been doing some work since then to sort of weed out sort of what we would call fake young objects. These are objects that have infrared properties that make you think that they're very early in their evolution, but in fact, when we go and look for the evidence of that with dense gas, we find that some of them are actually not what they look like. And this is the original sample, sort of invisible here. And then if you weed out the ones that are bogus, that's the red sample. And here's this AV of 8 threshold. So the relationship gets even tighter once you weed out what we call the misfits. And this is a paper we just submitted. So if you plot these in the more usual way, star formation rate versus log of the mass of dense gas, these are the local clouds, and these are those high mass, more distant clouds that are measured. Everything's measured in a different way, but they fit on the same relationship. And those fit on the same relationship as the Starburst Galaxies. So I'll sum up by saying that stars form in the dense parts of molecular filaments. Massive stars apparently need even higher density. The star formation rate looks linear once you count the mass above some threshold. And those relations extend from the nearby clouds, where we can count the YSOs, all the way to Starburst Galaxies. Now, I don't mean to say this is the entire story, because one has to suspect that there are multiple bottlenecks to turning gas into stars. On the cosmic scale, you have to supply gas to the galaxy. And presumably that's what's causing the peak in star formation rate at Z of 2, or sorry, about 10 gigayears ago. Within galaxies, you've got to turn atomic gas into molecular gas. We've seen that the stars form in molecular gas. The Milky Way, for example, has a huge atomic gas reservoir at large radii. There's enough gas there to form stars at the current rate for 6 gigayears. It's not doing anything. So until that gas gets turned into molecular gas, probably by being disturbed and coming in closer to the center of the galaxy, it's not doing any star formation to speak of. But it looks like now there's a second requirement. You've got to turn that molecular gas into dense gas. If we look at on the detail of where stars form, we see that they're very highly concentrated through filaments, which are greater than a surface density of about 120 solar masses per square parsec to be quantitative. Now, I'm sure that there are other factors involved, even in this last step. There's nothing really magic about a certain surface density threshold. It's bound to depend on things like how strong is the turbulence, how strong are the magnetic fields. It's going to depend on the metallicity, how many heavy elements there are. So I don't want to imply that this is the end of the story, because I think that's just a hint that we need a deeper theory and a deeper understanding of star formation if we're going to understand the conversion of gas into stars on all of these different scales. So I'll stop there and see if you have questions. Right. Right. So these are based on our Spitzer data plus 2mass data. So we're able to go to essentially 8 microns all the way down to 2 microns, and you get the extinction at the longer wavelengths, and then you have to assume some model to turn it into A sub D. And the model that seems to work in the molecular clouds is technically the RV of 5.5 model of Weingartner and Drain. For molecular clouds, the dust has already grown compared to the general interstellar median. So I always sort of wince when I hear people talk about Milky Way dust. There's no such thing. There's a lot of different dust particles. That's right. Yeah, and they're bigger in molecular clouds. Ah, yeah. Okay. So I'm sorry. I should explain. So 22 micrometers, and we call them microns for bad reasons, is the wavelength of the light. So the 22 microns, or micrometers, is primarily emission from dust, pretty warm dust. So when you make a bunch of stars, if they're massive enough, they'll ionize the gas around them, and then you will get emission in hydrogen alpha. You'll get radio continuum emission from free processes. You'll get a whole bunch of indicators. And the stuff around that, the dust around there, gets warmed up and emits at these wavelengths around, well, emits at a whole range of wavelengths. Turns out we talk about 22 or 24 micrometers because those are the wavelengths of bands on Spitzer and WISE. So we have images of these regions at those wavelengths. And they're used a lot in the extragalactic community to measure star formation rates. So we're kind of testing at that level. Okay, so the efficiency of 0.01. There are a few theoretical papers which try to claim they can justify that. But the problem is they knew the answer before they started. And if you simulate, people do smooth particle hydrodynamics or adaptive mesh refinement hydrodynamics, and they almost always get higher efficiencies of star formation. Some of the most recent simulations are starting to slow down star formation to get at least in the ballpark of that number of 0.01. But that's the puzzle. We don't really understand why star formation is so slow and so inefficient, even at the level of an individual cloud. No, it's really, we get that even in a whole molecular cloud. You get something like that. So to my mind, there's two problems. One is that the free fall time is probably not actually that relevant. And it's a problem that, you're averaging the density and then you take the square root and take 1 over that. And in fact, because it's 1 over the square root of the density, what happens is the denser regions are the ones that actually have a shorter time scale. So most of the cloud is kind of diffuse and not doing very much. The whole cloud doesn't seem to collapse. It's only little localized regions within the cloud that actually achieve a density at which they collapse. And what's resisting that is probably some combination of turbulence and magnetic fields. But when people do simulations of turbulence, even with magnetic fields, they tend to decay pretty fast. So we still do not have a real understanding of what is slowing down star formation to this kind of 1% number. Yeah. No. I think, I prefer to say, here's the facts, guys. Now, you theorists, you explain this. I think if you think about star formation as a collection of these entities, then if you just add up more of them in a linear way, and you get a certain amount of star formation for each one of those, you can kind of see why it would be linear. But why in this whole complex of turbulent molecular cloud, it winds up being that it depends on this fraction that's dense, and then that fraction turns a constant fraction of itself into stars, I think is not really understood. Mm-hmm. Yeah. Okay, so the question is, you have molecular gas. It goes through, we saw that the molecular gas is sort of concentrated in these spiral arms. If you look closely, you notice that the star formation tracers were offset a little bit. And so there's stuff passing through these spiral arms. They're not solid things. It's a wave that's passing through. So the stuff's getting compressed, and the question is, can we explain that offset? And that's sort of the question. There's also a fact that you see where you make a lot of stars, you will see maybe that triggers a lot of star formation nearby. And that is another way of explaining the sort of following spiral arms of the star formation rate. And I think that's another aspect. Most people figure that orchestrates star formation. It concentrates it in certain areas, but it doesn't seem to actually be what controls the rate of star formation. It's more of an organization within the galaxy. But all this stuff, I think, needs to be re-examined with, the vast amount of new data that's available. But that was the consensus the last time I checked on that. The filaments, the things I was showing you were observational. There is now a lot of theory. People are doing these turbulent simulations, and they're getting filaments that have many of the properties that are observed. So I think the fact that the filaments are ubiquitous in the molecular clouds is triggering a lot of new good theoretical work that might help lead us in the right direction.